These sampling distributions...
The Seattle Epidemiology Research and Information Center, in collaboration with the Department of Veterans Affairs, the VA Employee Education System, and the University of Washington Department of Epidemiology, present the 2002 VA Epidemiology Summer Session.
Good day. My name's Gail Reiber. I'm the director of the VA Summer Epidemiology Program. I'd like to welcome you all back to our General Biostatistics course. Professor Marie Diener-West is our faculty. She's a professor of biostatistics at the Bloomberg School of Public Health at Johns Hopkins University. And Dr. Diener-West is going to continue on today addressing common statistical methods. Dr. Diener-West.
Thank you. Well, today where I'd like to begin is by reviewing some material. And where we've been over the past few lectures is looking at the common methods of statistical inference that use estimation or hypothesis testing. So I wanted to just review with you that there are a number of ways of estimating. One is the simple way of obtaining a point estimate from our data. So in other words, a point estimate is no more than just the value that we derive from our sample data of the sample statistic. So some common examples of this are that X bar, known as the sample mean, is the mean or average, for instance, age in our data set. If we had two groups and we were interested in the difference in mean age between two groups, say males and females, the sample statistic of interest is the difference in sample means, X1 bar minus X2 bar. Some have asked, how do I know whether I should be looking at means or at proportions? It really depends on whether the variable of interest is a continuous variable, such as age, or whether it's a dichotomous or a binary variable. We can all think of binary variables, such as success, failure, response, non-response, but it is also true that different continuous variables can be made into binary or dichotomous variables. So, for instance, if I was interested in the proportion of individuals that were above age 18, because 18 was a threshold that had been shown in previous studies of some sort, I could look at the proportion of individuals above age 18. That's now a binary variable because the person is either less than age 18 or above or equal to age 18. So then our sample statistic of interest would be the sample proportion p hat. And again, if we had two groups, such as males and females, I may be interested in the difference in the proportions of individuals who are above age 18 between males and females. And then the sample statistic of interest is this difference in sample proportions. So fortunately, we can use the same variation on a theme to talk about one group or two group comparisons, whether it's continuous data or binary data. So the point estimate is just the value of the sample statistic. These are four examples that we might get from our study, from our data. The second level of estimation is to form a confidence interval estimate. So to actually take the point estimate that we get, the sample statistic, and form an interval around it that gives us some level of certainty regarding the true value that we're trying to estimate from the population based on our subset or sample of data. So the general form is to take the value that we obtain from our data, the sample statistic, form an interval around it by adding and subtracting z or t times the standard error of the sample statistic. So again, we had a variation on a theme depending on whether we had continuous data, such as mean age in one group, and we could form an interval around that sample mean by adding and subtracting a t times the standard error of the mean, that's s over the square root of n. We expanded that to the two-group comparison. For instance, the difference in mean age between males and females. Again, we would take the sample statistic, add and subtract t, times a standard error that depends on both the sample variances from both groups as well as the sample sizes from both groups. And although we didn't focus on this on proportions in as quite as much detail, if we were interested in the proportion of individuals above age 18, we would take that sample proportion based on our data, form an interval around it by adding and subtracting z times the standard error that's based on p hat, the sample proportion, q hat, which is just 1 minus p hat, and the sample size n. And lastly, this could be expanded to the final scenario where we're looking at differences in two proportions, and we would take the difference in the sample proportions, form an interval around it by adding and subtracting z times the standard error that again is dependent on the sample sizes n1 and n2 and the sample proportions p1 hat and p2 hat. So these are not things that need to be memorized. I'm really showing you these just to illustrate the fact that this expands to these 4 different situations in which all that we need to know is the sample statistic that we calculate from the data and the standard error of the sample statistic that we again estimate from the data based on sample variances and sample sizes. Does this make sense? So it's a variation on the same theme. The confidence interval now gives us a range of values from a lower limit to an upper limit that allows us to say we're 95% confident, based on our data, that the true value falls somewhere in this range. And it may be narrow, it may be wide, depending on a couple of things. What things? Sample size in particular. Sample size in particular. And the amount of variability in the data. So estimation was this one form of making a statistical inference. The other was hypothesis testing. So again, we can talk about this in general form. And the general form would be that we have a null hypothesis of some sort, in which we're stating that the true population parameter, the one that we are not able to measure, but the true population parameter is equal to some hypothesized value. So what could that true population parameter be? We've looked at 4 scenarios. It could be the true population mean, the true difference in 2 population means, the true population proportion, the true difference in 2 population proportions. But our hypothesis is that the value that true population parameter takes is some hypothesized value that we have hypothesized based on what? Well, the null hypothesis is one that we're phrasing based on our knowledge from either previous studies, pilot studies, or if we're really interested in a 2-group comparison, often it is a null hypothesis that the difference between 2 means or the difference between 2 population proportions is equal to 0. So, but we're always phrasing this as a null hypothesis of some hypothesized value, and often that hypothesized value is 0. So how do we, what is the basis of hypothesis testing? The basis of hypothesis testing are these theoretical sampling distributions that we talked about, in which if we had the ability to take all possible samples of a certain sample size, then there would be a normal bell-shaped curve that depicts a histogram or relative frequency distribution of the possible values of the sample statistic when we assume the hypothesized value is true. So what does this mean? It means that we can talk about making a hypothesis about the true population mean and construct a distribution that reflects all the possible values that the sample statistic x bar may take. So if the hypothesized value is in the center of this distribution, then the values that are of the sample mean that are likely, or the ones with high probability, are those that are close to the hypothesized value, right? Whereas ones that are far in the tails of the distribution are unlikely values of the sample mean if the hypothesis is true. So we're hedging our bets a bit, and we're making a guess about the true value in the population, and we're looking to see where our observed sample statistic falls in that range of possible values. So that if our value falls in the middle of this distribution where there's high probability, we would say that it's still likely that we sampled from a population in which the true value of the mean was the center of this distribution. If our observed sample statistic, on the other hand, was out here in the tail of the distribution, what would we conclude? That it's unlikely. So in other words, we've sampled from a population that has if it's out here, has a higher mean. If we observed a sample statistic out here in the other tail, we'd conclude that we've sampled from a population that has a lower mean. And we can do this with all four scenarios: a single sample mean, two sample means taken from two independent samples from two independent populations, or a single population proportion, or a different, where we're sampling one sample proportion, or a difference between two sample proportions taken from two independent samples from two independent populations. So what we would like to be able to do, though, is calculate these probabilities. How likely is it? Is this observed sample statistic have a high probability or a low probability? So we always then can transform the distribution for this sample statistic to a z or a t. And we know that those, the standard normal distribution or the t distributions, are tabled. Those are ones in which if we transform the observed sample statistic by subtracting the hypothesized value and dividing by the standard error, we now have a new z or t, and we can see where our test statistic falls in this distribution. So the probability of observing this observed sample statistic is the same as the probability of observing this test statistic. Same probability. So we can think of these likely values of the sample statistic as ones that would fall in the acceptance or the fail to reject region for the test statistic. Otherwise, the unlikely values of the sample statistic correspond to the rejection region, the very low or the very high values of the test statistic. So how do we make conclusions then and statistical decisions? We would say that if the test statistic falls in the rejection region in either tail of this distribution, in that case we also know that if it falls in the rejection region, and if we've also set the significance level to 0.05, then what do we know about the probabilities out here in the tails of the distribution? If the overall significance level is 0.05, then the probabilities in each tail are 0.025, so that we know that the p-value, which is the probability of getting the test statistic that you observed or something more extreme, if the test statistic falls in this rejection region, the p-value would have to be less than 0.05. So falling in the rejection region, having a p-value less than 0.05, means that this value of the test statistic, which corresponds to the observed sample statistic, is unlikely to occur just by chance alone when the true mean is equal to this hypothesized value. On the other hand, if the test statistic falls in this acceptance region, that corresponds to an observed sample statistic that falls in the likely category. Here the p-value would have to be greater than 0.05, and what would we conclude? That it's likely that this value of the observed sample statistic is likely to occur when the null hypothesis is true, when this hypothesized value is true. And in that case, then we'd say that it's likely that we sampled from a population having a mean of that same hypothesized value. Okay, so these two overheads were just an attempt to try to place this all in the same perspective. That all that we're doing is really repeating either setting up a confidence interval or setting up a hypothesis test under different scenarios. So now why don't we spend some time reviewing homework 3, and in particular we should be able to review the first problem pretty easily because we talked about this yesterday. So if you looked at it again last night, the question of interest here, the scientific question, and remember all of our analytic procedures are going to always refer back to some scientific question. The scientific question was, does nervousness that's presenting upon seeing a dentist elevate blood pressure? So there was a study, remember, of 60 subjects, and blood pressure was measured in a dental setting, and then for those same 60 subjects, blood pressure was measured in a medical setting. So first of all, we'd have to say, what kind of an outcome measure do we have, continuous or dichotomous? How many of you would say continuous? You're right. It's continuous because blood pressure is measured on a continuum. We aren't looking at whether it exceeded or fell below some threshold. So we would have 60 continuous measures in a dental setting, 60 in a medical setting, and then of interest is whether or not when we use an individual as their own control, whether there's a difference in the blood pressure measurement between dental and medical. So the data that we were supplied with is that the mean difference, so each of these differences were calculated, and then the average of those differences is the mean difference, was 4.47 millimeters of mercury. And the standard deviation based of the differences, so the standard deviation or the variability in those differences was derived as 8.77. So we could construct a 95% confidence interval for the true mean difference in the population of all individuals who may have their blood pressures measured in both a dental and medical situation. And again, we'd form this by taking the sample statistic. Here's our sample statistic, the mean difference of 4.47 millimeters. And we'd add and subtract the t statistic that corresponded to an alpha of 0.05, split into two tails, with 59 degrees of freedom. We saw that this was close to 2. And then the standard error of the mean difference takes the standard deviation divided by the square root of n. And we found an interval that ranged from 2 up to 6.7 millimeters of mercury. How do we interpret that? How about somebody offer to interpret it? The answer was that we could interpret this confidence interval that falls above 0 in a positive direction from 2 to 6.7 to indicate that there appeared to be a higher blood pressure expressed in the dental situation than in the medical situation. So this interval ranging from 2 to 6.7, I'm 95% confident contains the true difference between the dental and medical measurements of blood pressure. Now, if this had included 0, what would I conclude? So if this interval contained 0, we wouldn't be able to conclude that there's a difference at all. The fact that we see this all in a positive direction indicates that there is a statistically significant difference between dental and medical measurements, and our data are indicating that it's higher in dental than in medical. On the other hand, if these had been negative values, so if this confidence interval had ranged from -2 to -7, we would have concluded that it appears to be lower, blood pressure appears to be lower in dental than medical because the difference was in the negative direction. Okay, so that's one way of trying to answer that scientific question of does nervousness at seeing a dentist elevate blood pressure based on the confidence interval it appears to. The other way is to set up a hypothesis test. Here, the null hypothesis is that the mean difference is equal to 0. The alternative is that the mean difference is not equal to 0. And we could then set up a rejection region and acceptance region for the test statistic. Here, the degrees of freedom we remembered were 60 minus 1 or 59. So that t statistic that corresponded to 0.025 in one tail of the distribution was 2. In the other tail, it's -2. So any values of the test statistic that fall above 2 or less than -2 would form the rejection region. Those that fall in between would form the fail to reject or acceptance region. So how's that test statistic formed? We take the mean difference, that's our sample statistic, minus the hypothesized value of 0, divide by the standard error of 8.77 divided by the square root of the sample size. And what would we get? What did you get? 3.94 falls here out in the tail of the distribution. So based on that, it falls in the rejection region. We'd conclude that this difference of 4.47 is unlikely to happen by chance alone if the true difference is 0. And again, we'd conclude that we'd reject the null hypothesis and conclude that the mean difference between dental and medical blood pressure measurements is something other than 0. What's the p-value? The p-value is based on our observed test statistic. So the p-value is the probability of observing a t of 3.94 or something bigger, or in the other direction, a t of negative 3.94 or something smaller. And because it falls out there in the rejection region, we could use the table or use a statistical analysis package to get a more precise p-value, but we know it's something less than 0.05. Okay, so just as review, we've concluded then based on the p-value, based on the fact that the test statistic fell in the rejection region, based on the confidence interval, all three of these would lead us to the same conclusion, that there appears to be a higher blood pressure in the dental setting than in the medical setting. Okay, so let's look at another problem. This was a sample of 1,000 adults in the Los Angeles area. They were all measured with an instrument called the CESD depression scale. And it's a scale that goes from 0 to 60, from least depressed to higher depression. And the information that was given to us was that there were 412 males, 588 females. The means were calculated as 7.6 and 10.4. What type of data do we have? A continuous outcome. So here are the sample means for the males and females respectively, the sample standard deviations of 7.5 and 10.3. Now, just to add another column here, we had some discussion yesterday regarding standard deviation and standard error. So here, this is just the sample standard deviation for each group, S, the square root of the sample variance. The standard error, on the other hand, takes S divided by the square root of the sample size. So if we have standard deviations of 7.5, we're going to have a much smaller standard error because we're dividing by the square root of 412, and the same for females. Okay, so standard deviation expresses what type of variability as compared to the type of variability that standard error represents? Anyone? Don't raise your hands all at the same time. So just if we were simply to say, what does the sample standard deviation reflect in terms of variability versus what does the standard error reflect, what would you say?
The standard deviation represents the precision of the measurements, and this standard error takes into account the sample size.
That's right. And so let me just add to that, that the sample standard deviation reflects the variability that's present in those 412 measurements of the depression in males. The standard error, on the other hand, reflects the variability in all the possible sample means that we might be able to get taking samples of size 412 from a population of males. So standard deviation represents variability in measures. Standard error represents variability, in this case, in the means, in the possible means. And that's why it's so much smaller. So what's the scientific question of interest? The scientific question is, does the mean or average CESD score differ by gender? So I'll just express what's given in the table in a different way. We have two sample sizes, N1 and N2, representing males and females. We have two sample means, one for males and females, 7.6 and 10.4, and two sample standard deviations, 7.5 and 10.3. So I could set up a null hypothesis that the difference in the true population means is equal to 0 versus an alternative hypothesis that the true difference in means is not equal to 0. How would we set up then a rejection region? Sample sizes are pretty big. In theory, it would be a t statistic, The sample sizes, though, are so big that for all practical purposes, the rejection region could be defined by a z, where we place 0.025 in each tail of the distribution. So the rejection regions are those values that are z greater than 1.96 or less than negative 1.96. The likely values are those that fall in this acceptance region in between. So again, the t-statistic is going to take the difference in the sample means, that's our sample statistic, minus the hypothesized value of 0 divided by the standard error. So most of you are not going to have to calculate this by hand. Most of you are just going to interpret the test statistic at the end, which in this case is negative 4.97. Where does it fall in this distribution? Far out in the left tail of the rejection region. And again, as I said, since the degrees of freedom are so large, 1,000 minus 2, or 998, we can assume that for all practical purposes, the t is the same as a z, and we'd conclude that we'd reject the null hypothesis, that there appears to be a difference in, that we've sampled from two different populations. The males and females have different mean depression scores. The p-value, well, it's so far out here in the tail of the distribution, the p-value, or the probability of this value, or something more extreme in either direction, is approximately 0. So again, the p-value would certainly cause us to reject the null hypothesis. And our conclusion, we'd conclude that the mean depression score appears significantly, statistically significantly higher in females. Now, how can I say it appears to be higher in females? I have to go back and look at the data. So without looking at the data, since this was males minus females, I got a negative test statistic that would clue me in. But also I'd go back and see that the female mean score is higher than the males. And you may have not calculated this at home, but we could alternatively look at a 95% confidence interval for the true difference in means between males and females, mean CESD scores. We take the sample statistic, form an interval around it by adding and subtracting. It's really a t, but remember the degrees of freedom are so big that we could use the z value of 1.96 times the standard error. If I go through the math, I end up getting a confidence interval that ranges from negative 3.9 to negative 1.69. And again, the conclusion would be that this 95% confidence interval, I feel 95% confidence interval that this range contains the true difference. Does it contain 0? No. Now, this confidence interval provides us with a little bit more information than we got from the hypothesis test. This tells us that the difference between males and females may be that the mean score is approximately 4 points lower on average in males than females, up to approximately 2 points lower. So this is where the judgment has to come in as to how critical is a difference of 2 to 4 points on this scale. So for certain scales, this might mean, in a practical sense or a clinical sense, quite a bit. For other scales, it might not. So for instance, on the SF-36, a difference of 5 points is considered to be clinically meaningful. So this is where some judgment comes in. It is statistically significant, but we had very large sample sizes, 400 in one group, 500 in the other. So some judgment needs to come in terms of that practical interpretation. Any questions so far? Is this exactly what you did at home last night? Good. So one more question, and that was looking at some data of an epidemiologic investigation at a high school in which they were looking at positive tuberculin reaction, and there were those that were exposed to some to a tuberculosis antigen and those who were not. So there was a high versus low level of exposure. There were a certain number of individuals who were tested, and then you were given information about how many tested positive. So here, again, we'd have to ask the question, first of all, what type of data are we dealing with? Is it a continuous outcome measure or a binary or dichotomous outcome measure? Binary, because one could test either positive or negative. So we would really be interested then in proportions, because it's a binary outcome. And the proportion positive was 63 over 129, or 0.49 in one group, 36 over 325, or 0.11 in the low exposure group. So on the surface, we're interested in seeing whether there's an association between exposure and testing positive. So on the surface, what would you say? Yes, because there's a higher proportion testing positive, almost 50% in those with high exposure versus 11% in those with low. So our aim is to compare the proportions with a positive reaction. And how might you take this information and set it up in a way in which one could calculate a chi-square statistic? 2-by-2 tables. So if we set up a 2-by-2 table, we were given the total number tested. We put those on the row totals. We were told the number positive in each. So in the high exposure group, 63 tested positive. That means that 129 minus 63, or 66, tested negative. In the low exposure group, 325 were tested, 36 of whom tested positive. So 325 minus 36 means 289 tested negative. And then we can add the total positives, the total negatives, and we would consider then the cells of this table as A, B, C, and D for the shortcut formula. So we're really interested in whether what we've observed in this table is what we would expect if the true proportion that tested positive was the same in both groups. So we could go through the longhand way, couldn't we? Should we? No, because we have a time saver. But if we went through the long way, we would say that overall, 99 out of 454 were positive. So it's that proportion of the 129 we'd expect to be positive. It's that proportion of the 325 that we would expect to be positive. But I agree with you. Let's go for the shortcut formula. So if we use the shortcut formula, our hypothesis of interest is that the difference in the two population proportions who test positive is 0 versus an alternative that it's not. And then we would just plug in our numbers into this shortcut formula for the chi-square. So the overall total was 454. We would take A times D minus B times C, square it, and then divide by the product of the column totals times the row totals, and we would get a chi-square of 77.2, 1 degree of freedom, because 2-by-2 table always has 1 degree of freedom. And we would compare that to the tabled value in the chi-squared table of 3.84, which corresponds to a rejection region of 0.05 and 1 tail. So we certainly know that our value of 77.2 is far different from 0, far out in the rejection region of this distribution. Okay. So, questions on that? No? Okay. So, I put in a little bit more detail than you needed to for the homework, but hopefully you reached the same conclusions with it. Okay, so now what we're going to do is look at our topic for today, which is comparing more than two groups. Up to this point, we've looked at only comparing two groups, either males versus females, treatment A versus treatment B, for both means and binary outcomes. Today, we'll be looking at comparing means among 3 or more groups, as well as comparing distributions of 3 or more groups. In other words, we could compare proportions among 3 or more groups, or if we had more than 2 levels in a category, we could compare the distributions of 3 or more categories across 3 or more groups. Okay, so our first topic is going to be comparing means among 3 or more groups. And the method that's commonly used for comparing means is actually one that appears at first glance to be a misnomer, because it's called analysis of variance. But in fact, we use the analysis of variance to help us assess whether there are differences in means between 3 or more groups. So we'll outline the basic principles of analysis of variance. We'll look at how the F-test is used, and then we'll look also at how we can use multiple comparisons testing to see which of the pairwise differences in means between groups are different. Okay, so an analysis of variance is a method for testing a null hypothesis that the underlying population means of k different groups are the same. So the null is that the underlying population means are all the same, versus an alternative that at least one of the population means is different. So here's our aim to test this hypothesis. The technique that we'll be using is to compare means from multiple samples by actually partitioning the total variation into a data set into different components. So we're going to test means by looking at variability. And there are several assumptions that are needed. The assumptions are that we again assume that we have independent observations, so independent people or observations. We'll also assume that we have equal variance or equal variability in measurements across observations within a group. So you might say, well, is this always true that there's equal variability in groups? Is the variability always the same in treatment A versus treatment B versus treatment C? It might not be, and we sometimes have to assess whether that assumption is accurate or not. If we can't make this assumption, I'll mention several other techniques that could be used. So just as an introduction, analysis of variance is really a global test for differences in means. In other words, remember what the null hypothesis was. It was that the mean for population 1 is the same as that for population 2, is the same as that for all k populations. So it's a global test. And if we find a statistically significant result in this global test, which we'll see is called an F-test, it's only then that we'd be interested in seeing whether there are pairwise differences among groups. Otherwise, if the result of our global test indicates no statistically significant difference, we would just conclude that the null hypothesis appears to be true and all the means appear to be the same. So we only need to look at pairwise comparisons of means when we reject the null hypothesis with the F-test. And then we'll see that there are procedures called multiple comparisons procedures that we can use. So that's our framework. Now, what's the underlying rationale? I could spend a couple of hours detailing for you what the underlying premise of analysis of variance is and give you a lot of formulas for this. I think I'll skip that part today and mainly indicate that we're interested in expressing the total variation, the total variability in a data set as two parts. We can express it as how much variability there is between groups and how much variability there is within groups. And the F-statistic, the F-test statistic, is really just a ratio of the estimate of the variance that's based on between group differences, what we'll call the mean square for between groups, compared to the denominator, which measures the variability based on within group differences. So this F statistic is just a ratio. Now, let me try to take you through an exercise. If there was just as much variability between groups as within groups, what would you expect this F statistic to look like? 1. It would take on values near 1. Now, if there was a lot more variability between groups than within groups, this F statistic would take on very large values. So if we think of variability in groups, so here's group A and has some variability. I'm trying to pretend I'm an applet right now, but there's some variability in group A and some variability in group B and some variability in group C. But if the variability that's between groups is the same or no bigger than the variability within, what do you expect about those mean levels? They'd be about the same. Now, if there was more variability in one group than in another group, and we had some other group over here with other variability, what would you expect about the mean levels? Different. So if the variability extends up in one group, we'd expect the mean to also extend. So the whole premise is that we're looking at this F statistic to see whether there's more variability between groups than within. So as I just said, but I will state in a different way, a large F statistic would indicate more variability among groups than within. Then we'd reject the null hypothesis, conclude that at least one of the group means is different, whereas F values that are near 1 would indicate similar variability among groups as within. And this would be a situation where we would not be able to reject the null hypothesis. We'd conclude that the group means appear to be equal. So our main aim is to interpret this F statistic. So an F statistic near 1, we'd conclude that the means are equal, and we don't have to do anything else. Our conclusion is that at least is based on the F statistic, that based on our data, the means of the populations that we sampled from appear to be the same. Whereas if we have a very large F statistic, we'd conclude that at least one of the group means is different, and this is where we'd perform a multiple comparisons test. So there are lots of different types of tests. One is a Bonferroni adjustment that we'll talk about in a while. Other ones are given some interesting acronyms, again attributed to John Tukey, who gave us the stem and leaf and box and whiskers plots, but the LSD is the least significant difference. The HSD, also attributed to Tukey, is the honestly significant difference. So both of these are aiming to get at what are differences between groups that aren't found just due to chance alone or aren't a result of increased type 1 error. And then there are, I could list a number of other types of types of multiple comparisons procedures. Okay, so let's just, before we go to an example, just indicate why we would perform a multiple comparisons test and the benefit of it. So if our F statistic is large, we reject the null hypothesis and conclude that at least one mean is different. What we're really interested in is if we have multiple treatment groups, which treatment groups are different from each other. We'd like to know, is treatment A different than B? Is B different from C? Is A different from C? All that we know from the F test is that at least one of them is different. The problem with making multiple t-tests is that consider each t-test, we set the significance level of 0.05, alpha of 0.05. We're trying to minimize our type 1 error at 0.05 for each test, each separate test. If we perform multiple t-tests, multiple separate tests, we'd actually increase the probability of a type 1 error above 0.05. So just by chance alone, the more comparisons we make, the more t-tests we perform, we're likely to find one to be significant or more to be significant just by chance alone. So the aim of any multiple comparisons procedure is to preserve the overall alpha level. In other words, at the end of the day, we would like to be able to say that we've kept the probability of a type 1 error minimized at 5%. So the multiple comparisons procedures are an attempt to keep that level at 0.05 and not increase it above that. Okay, well, I've given you a lot of the setup, but I think we should look at an example to try to make sense of this. This is actually your homework example for tonight. So we're going to look at your homework, one of your homework problems today, and review this. So this was an example in which there was a scientific question of interest, and that scientific question of interest was whether smoking influenced mean serum testosterone levels in men who are aged 35 to 45 years of age. So in other words, the question of interest is smoking associated with mean serum testosterone levels in these middle-aged men? So here we have the mean or average testosterone levels, and we see it for 4 groups. Non-smokers, these are men who had never smoked. Former smokers, these are men who had quit for at least 6 months prior to the study. Light smokers, they smoked 10 or fewer cigarettes per day. And then heavy smokers, they are men who smoked 30 or more cigarettes per day. So this was a study that was based on these 4 groups. You might say, well, there may have been smokers in between light and heavy. I think they were excluded from the study. So there were 4 groups, and there were actually 10 men in each group, and these are the averages. So based on the overall data, the mean testosterone level was about 0.6 micrograms per deciliter. What do you notice by smoking category? Any relationship? So doesn't it appear that if you go from non-smokers to heavy smokers, you actually see a trend? The testosterone, the mean testosterone level seems to decrease as smoking increases. So our data are telling us that there appear to be differences between these groups. If we inspect this a little bit more just by looking at it, in fact, is there a difference between non-smokers and former smokers? Not as much of one, but we see a drop when it comes to light smokers, and we see a more substantial drop when it comes to heavy smokers. So certainly there appears to be a difference on the surface between non-smokers and heavy smokers. So how would we look at this in an analysis of variance? This is an analysis of variance table. All that I'm going to actually ask you to focus on is the F statistic that we see here and the p-value, though I could take you to these other parts as well. The other parts are giving us what's labeled here as a mean square. It's just giving us an estimate of the variance based first on between group differences and secondly based on within group differences. So you can see that the within group variability is less than the between group. 0.02 is less than 0.113. But the statistical measure is the F test. It's a value of 3.8. Is it bigger than 1? Yes. How much bigger than 1 depends on the degrees of freedom. Here we had 4 groups, so 3 degrees of freedom in between groups. We had 40 measures altogether, 40 observations, so the total degrees of freedom were 39. This F statistic is actually going to be based on the degrees of freedom you see here, 3 and 36. But you can do more reading if you wanted more detail on the analysis of variance and the separation of variation into these 2 components. Right now, let's just interpret the F statistic. It's a large F. The probability of observing this F, if there was no difference in mean testosterone levels between the 4 smoking groups, is about 0.018. So if our null hypothesis is that all the means are the same, what would we conclude based on this F test? We'd reject the null hypothesis and conclude that we can't conclude that all of the means are the same. We'd conclude that at least one is different. So again, if you thought of doing individual t-tests to compare non-smokers to heavy smokers, non-smokers to light smokers to heavy smokers, how many different comparisons would you have? You'd actually have 6, and they're actually all 6 of them are listed here. So this is a Bonferroni corrected p-value that's given by Stata that allows us to look at a comparison here of former versus non. The p-value is the second value. What's the first value? It's the difference in the means. So remember, former smokers and non-smokers had very similar mean testosterone levels. What's a comparison of light versus non-smokers? Again, the p-value is not statistically significant. Light versus former, the p-value of 0.953 is not statistically significant. But you'll see in the comparison of heavy smokers to non-smokers, the p-value is less than 0.05. As well, comparing heavy to former, the p-value is less than 0.05. So I'm hoping to show you with Stata another way how we can interpret this. But the main thing is that this second value is a corrected, it's a multiple comparison corrected p-value that's aiming to keep the overall type 1 error minimized at 5%, even though we're making 6 different comparisons. So what I've underlined are the significant p-values indicating differences between non-smokers and heavy smokers, differences between former smokers and heavy smokers in mean testosterone levels. Here's the editor, just to show you. I set up those 4 smoking groups from non-smoker to heavy under smoke group 1 through 4. And then serum testosterone levels are in the second column. So I just entered that into the editor. So wonder if I wanted to explore this. I could say graph those serum testosterone levels by the smoking group just to sort of look and see in another way. We looked at means already, but how about if we look at this graphically? So here's the box plot. In fact, let me give you just a little bit better label. Okay, here's the box plot. So remember, these were non-smokers. The next group was former, light, and heavy smokers. So what do you notice about median testosterone levels? They're similar in the first 2 groups, but they decrease with increased smoking. What about the variability in these groups? Pretty much the same. Pretty much the same. Actually, we're looking from the maximum down to the minimum. Those are pretty much the same, maybe a little bit more, a little bit higher. But for the most part, the variability is about the same. But what do we see? We see the medians decrease with increased smoking. We could also close this graph and then look at summarizing by smoking group serum levels. And so here what we see are 10 observations in each. We see the means that we saw in the previous slide that went from 0.687 down to 0.682, 0.571 to 0.463. We see the standard deviations are actually all about 0.2, and then we're also given the minimum and the maximum. So we'd want to first look at the data, see if we see any trends, and then the command that we would use for what's called a one-way analysis of variance, because we just have one group of interest, the smoking group, we could look at now the same table you see in the notes. I gave an option of means to repeat those means so we could look at them. There's the F statistic, the p-value that would cause us to reject the null hypothesis that all the means are the same. And there's one other thing here that's called Bartlett's test for equal variances. We eyeballed those standard deviations and said they were all about 0.2. Remember when we looked up here? They're all about 0.2. We eyeballed the box and whisker plot and said the variability was about the same. This is actually a test in which we'd focus on the p-value to see whether we'd reject a hypothesis of equal variance. In fact, the p-value is very large, so we can feel comfortable in assuming that the variability is the same in these 4 groups. So the very last thing is that I could also put Bonferroni as this option after the analysis of variance. And here's where we see the groups were labeled 1 through 4. So this table is comparing groups 1 to 3 versus 2 through 3, so that the p-values that are the second values here, if we looked at the comparison of group 4 with 1, that's the heavy smokers versus the non-smokers. The difference in the means is 0.46 minus 0.687. That's what negative 0.224 is. And the corrected p-value, adjusting for multiple comparisons, is the p-value of 0.038. So we'd say there are statistically significant differences between non-smokers and heavy smokers. As well, the only other statistically significant p-value compares heavy smokers to the group 2. Group 2 was former smokers. So if we compared heavy, 0.463, to the mean for former smokers of 0.682, we'd get a negative 2.19 with a p-value of 0.044. So the global test said reject the hypothesis, conclude that at least one mean is different. The Bonferroni test allowed us to indicate which of the means, which of the groups had means that were statistically significantly different. So this is where I'm going to stop. There's time for a few questions, if you have some, regarding this example that we just reviewed. I'm hoping that it makes sense that we look first at the result of the F-test as a global test, and then we're allowed to inspect these Bonferroni corrected adjustments to indicate the pairwise differences. Praveen?
Yeah, I have a question about Bonferroni. My impression was that anytime we use Bonferroni, it dropped the p-level.
Right. So the question was, when we use Bonferroni, what we're doing is that we're actually adjusting the significance level so that this p-value is actually already adjusted for the fact that we've made 6 comparisons. If we had done a t-test looking at at heavy versus non-smokers, the p-value we would have gotten would not have been 0.038. It would have been 0.038 divided by 6. So in fact, this p-value is already adjusted for the 6 comparisons that we've made. So Stata gave us the adjusted p-value, but our aim would be to use a much lower significance level to consider it statistical significance. In fact, we would have used 0.05 divided by 6 as our significant p-value, not 0.05. And this has adjusted it already so that it allows our eye to look at these and compare them to 0.05. Other questions?
I think you had alluded to the fact that the standard deviations among the groups were really different. That was a problem? Is that correct?
So if the standard deviations are different among the groups, it violates one of the underlying assumptions of using this method. So I'll take you back to this bottom line that says Bartlett's test for equal variances. So this is actually a statistical test that's testing whether the underlying variances in the 4 smoking groups are the same or not based on our data. And the p-value we'd interpret in the same way. If it was less than 0.05, we'd reject the hypothesis of equal variance. So here we can feel pretty happy with the fact that the variances appear to be the same in all 4 groups. Now, if I got a p-value associated with this Bartlett's test for equal variance that was less than 0.05, then I'd want to hang this up and go to another method. So for instance, there are non-parametric methods of analysis of variance that use ranks and don't assume the parametric distribution. Now, we're actually assuming that these are means that are continuous data that are normally distributed with equal variance. So this assumption of equal variance might not be met, and then I'd go to a non-parametric method. So there are assumptions that go into many of these methods, but there are ways of checking the assumptions. There are ways of checking whether there's equal variance, checking whether there's independence. There are graphical ways and ways of statistically testing this. And so, part of interpreting these types of methods are making sure that the assumptions hold.